Hello and welcome, everybody. Thank you for joining me here at this theater session. I kind of love this setting. It's very direct, so it's very interactive. So yeah, I'm going to give you a hands-on tutorial on our software tools for quantum computing. My name is Bettina Heim. I'm part of a small but very cool team at Microsoft that works on quantum computing and design software for it that you can then use to get started. In particular, we have this very cool series of self-learning tutorials that you can use to get familiar with our tools, but also with quantum computing and anything you need to know to actually write really cool algorithms. So some of you may have seen something along these lines, where you actually have this neat picture of what your program is. However, how many of you are actually developers? Can I just... Okay, physicists? Minority, sorry. So it's all about devs today, business, PMs, administration. Okay, I guess a few biologists then. So those of you who have opened the physics books may have seen this first picture of the circuit because it's very commonly used in kind of your college courses to explain you how you could compute. And if you have looked at early versions or are potentially working very low level, you may have seen similar diagrams for classical computing. So if you look, for example, at an 8-bit adder, it already looks pretty tricky, actually. And it's pretty hard to make sense of what is standing there. So the bottom line is there's kind of a reason why we don't use the pictures to actually code when we code for conventional computers. And I believe a lot of you are going to be a lot more familiar with the left-hand side that actually looks like code and is readable. So that's where we come in, because that's what we want you to use. And we want to make it as easy as possible for you to get started without having to look up all the physics background. You shouldn't need to worry about that. So for today, we are going to look into one of these self-teaching tutorials that you can download on our website and start to get familiar with. And I would live solve one. So I'm sorry, I'm going to take the joy of a single one. We have a bunch of them, about 8, I believe there are right now. So we're going to be solving one of them, but there's still plenty for you to do and for you to go. And I really hope that after the session today, you are very motivated, if you haven't done so already, to actually go to our webpage and download them. So now is a good time to take a picture of where to get them. So let's just get started right away. So I've already downloaded them to save some time. What you get if you clone our GitHub repo is a folder with a bunch of things in it. There are different tutorials that you can follow. And we've got a workspace. You can use them in Visual Studio Code or Visual Studio or any other IDE you like, but mostly we support those two currently. And I'm going to be solving them in Visual Studio simply for convenience. They kind of come with this unit testing format, so it's nice to work in Visual Studio. Each one of those tutorials has a README file in it. So let's just take a look first. That README file tells you some useful information. For example, here it tells you what you're actually going to cover in this tutorial. But it also gives you some recommendations on what you may want to solve first. You don't need to solve them in a particular order, but some things help if you start with them, so it will tell you what to do here. There are also a couple of very helpful links here, for example, that you can open and that will point you to our documentation here, where you find further details that may turn out to be very useful for actually solving these tasks. So katas, for those of you who don't know, is kind of a series of exercises that you can solve and check whether you solve them correctly that have increasing difficulty to teach you something. All right? So for today, I'm going to be your encyclopedia of basically what is on these web pages. But when you solve them on your own, it's always helpful to open the documentation that we have here. And if you ever want to know something, you can try and look for it and see, aha, there's something that measures. That sounds like something that I might need, right? And don't get intimidated by formulas. We have different people actually looking at them. So physicists here will prefer them in this form probably. But there's also other documentation, so you can also work quite fine without knowing that. And our PM made really sure that I show you this one quickly. It's a blog post that members of Microsoft that are not part of our team, though, have picked up because they just really love quantum computing. That is very helpful to actually get started. I'm going to show you at the end, I guess. So just follow the link, click through them. There are always good hints there. So this one told me here now it's a good idea to start with basic gates. What you're always going to have is a tasks file. So these are the tasks for you to actually solve. This is what we are going to be filling in. So you see there are bits and pieces that are missing. Each task has a number, and it tells you what you're supposed to do, what the input is, what the expected output is. It gives you some hints and examples, and the comments are usually quite helpful to know what to do. Then the test file and the test runner is something you can basically ignore. It's these unit tests here that will allow you to easily check whether what you typed is actually correct. So here, for example, being in the basic gates, if I run those unit tests, you see there's a whole bunch of them. What is supposed to happen is that they all fail, because I haven't done anything yet. And what you're supposed to do is make them pass. So at the end, you're supposed to get them all green. Sorry, I thought I had. Well, that's very helpful. Okay, not basic gates then. Let me just get the superposition. Sorry, I thought I had just run it before. All right. Going this way. Visual Studio Code. Sorry. So I hope this should be readable for you. So as you see, we're on .NET Core, so anything I'm showing here works on Windows, Linux, and Mac. And as you see, as it's supposed to be, we have 8 tests. 0 of them passed, because I haven't filled in anything, and 8 failed. So this is exactly what we want. Yay! First thing solved successfully, failing tests. Now we can actually make them pass. Now let me just switch to actually the basic gates. So this is the one that we wanted before. I apologize for the little interruption. And so, okay. This one is a nice one. Okay. So let's see if we can solve the first one. So the first one asks you, we get a qubit, which is in a 0 state. And you're supposed to construct a very particular state here. The interesting part about the state is just that if you were to measure the qubit here, when it's in this state, you've got an equal chance of the measurement outcome being 1 and 0, which is kind of fun. And for the purpose of teaching you, this one already gives you basically what you need to do. It just shows you how the kata itself works. It tells you, please type the syntax here. For those of you who are not familiar with Q#, you can learn the syntax. So we are just going to do that. All right. And then go again with .NET test. Sorry, I can make it bigger. Or I can't. And we see now we have one test that passed. Yay, we did the right thing. Okay, yes.
Can you please scroll out the code to make it bigger?
Yes, I am trying. And if somebody knows how to do that in VS Code, I would be very happy to hear it.
Control scroll. Control scroll.
No. Doesn't seem to be the case. I was kind of hoping for that. Visual Studio Code. So I apologize very much for that setup. So I hope it's somewhat readable. And then there's a minus state. So there are different fundamental operations that you could perform on your qubit. It will just bring it into a different state. So for classical computing, you've got 0 and you've got 1, and you can flip that bit. But that's pretty much everything you can do. For quantum computing, you can do a whole lot more. So imagine you have a sphere. You could visualize your qubit as being like a compass needle that goes from the center of that sphere to somewhere on the surface. As long as you don't measure, don't look at it, that compass needle can be anywhere on the sphere. So there's plenty of things you can do with it. Once you measure, it's like having a vertical axis through your sphere, and your needle needs to collapse to that axis. It's either going to point up or point down. All right? And when we do certain transformation, like applying this instruction, this operation H here, for example, what we actually did was take that sphere and just turn it so that it's now on its side. And if we measure, we still measure along a vertical axis, but now because we've turned the sphere, we now have an equal probability that our needle that previously pointed up and now points to the side collapses to up or to down. All right? So that's all we've done, just for those of you who are curious about more physicsy aspects. So the question here is again, okay, we still get a compass needle that points up, and we want to create something where the needle now points left. What we did before was making the needle point right. So what we can do then is do the same thing as before, but then actually just flip it. So X is just a knot. It's just the opposite. So we are going with that and running our tests again. And hopefully we'll now have 2 passing unit tests. Nope, we don't. OK, let's check. So switch it around. And now we've got 2 tests passing. So the little thing I did here, from a physics perspective, we don't care about global phases. Apparently the test does. For those who are physicists, you know what I mean. So, phase problem. I tend to be a little bit lax with that because, constants and signs and things like that, not usually something I care about. So anyway, now we've got 2 tests passing. Now let's see if we can do something more interesting with it, potentially. So how about actually creating something like this? Now this is a very nice state for a particular reason. Because maybe some of you have heard the story of Einstein and that he didn't really like quantum mechanics very much. And what bothered him most about quantum mechanics was that there were these particular states that things were supposed to have, where you could do something to one part of your system, and the other part of the system would immediately do the same, or the exact opposite. But that kind of coupling together would be immediate. And that really bothered him. He thought that was just nonsensical to him. There was always the speed of light. As it turns out, having this immediate interaction doesn't actually violate the theory of relativity. Because while the interaction for a quantum system is immediate, there's no way we can read out the information and process it as a human being in a way that would be faster than the speed of light. In order to process it, to read it out, we will always have to either transmit some classical information to make sense of it, or send the qubit itself, which is also limited and bounded by the speed of light. But it's still a neat trick. If you think about it, think of cryptography. You can literally have 2 pieces, like a rock here and a rock here, and if you get one thing here, you're guaranteed that the same thing is in the other rock. Key distribution. Isn't that fun? So let's see if we can actually get the state here. We are given 2 qubits, as it says here, and we want to create this very particular state. So what we are going to do is that we are first going to make our first qubit kind of rotate to the side, and then we want to make sure to force the second qubit to always have the same value as the first qubit. So this is this neat C0 gate that we have here. And what it does, it's in a sense, it creates entanglement. Entanglement is nothing else than this spooky interaction that I've just described to you. So let's see if this does the trick. And indeed, we have 3 passing tests. So there are only 8 more to go, but I won't do that here because I think our time here is pretty short, and I really want to give you the chance to ask you some questions. Apologies again for the technical difficulties, but give it a try. They're pretty easy to get running, and they're fun to solve. Yeah? You have to... The downloading, yes. Let me just give you that. So this is the feedback for our website, and this is actually where you can get these fun exercises. Yes. We don't currently offer a service to run algorithms. We do. You can always use Azure to actually use the simulators that are released open source, of course, and do larger simulations with it. So in that sense, that's available to you. We don't have currently a dedicated quantum service that we offer you. Anything else?
I found out how to make the font larger. Control plus.
Ah, God.
Change the size.
Yeah.
Did you see it from there?
Yes, I really need the 15 minutes for the next session, I guess, to figure out what went wrong here. I apologize, I come directly from the last talk, and I could have sworn I built it before. Anything else? Okay, then thank you for stopping by. I hope you still enjoyed it and are curious about trying it out.